Hi, it's Matthew Reed here from How to Repair Pendulum Clocks, and today we are making a new 24-hour date wheel for an early 19th century longcase clock. So when we look at the clock dial, we can see that the original 31 tooth date wheel is present, and its hand as well. However, when we look at the movement, although the 12-hour wheel that drives the intermediate date wheel is there, sandwiched between the great wheel and the snail, the 24-hour wheel, the intermediate wheel that sits on the post we can see, is missing. Now this is a common appendix operation, if you like, that we find on a lot of historic clocks like this. So our job is to calculate and make a new wheel to reinstate the function of the date mechanism on this clock. So we can count the number of teeth on the 12-hour wheel, which is 30, and as you can see, this wheel rotates with the hour hand, so twice in a 24-hour period, and we want our date wheel to rotate once in a 24-hour period. Therefore it has to have double the amount of teeth. So that's our first bit of data. The 24-hour wheel will have 60 teeth. The other two pieces of data that we want are the pitch circle diameter of the wheel and the blank or outside diameter of the wheel. Now the pitch circle diameter is the effective working diameter of the wheel. You can see here the wheels represented as plain discs, pitch circle diameter. Obviously without teeth on the wheels would just slip. So we add a piece to the tooth which is called the addenda or addendum. That's the extra bit outside the pitch circle diameter, and on the other wheel, the meshing wheel, that addendum has to fit into something, and that is called the addendum, which is the cutout effectively. So we want number of teeth, pitch circle diameter and blank diameter from which we're going to cut the wheel. So we can estimate the pitch circle diameter of the new wheel simply by holding up a ruler to the post on which it pivots and the wheel that drives it. And actually this way with historic work is often the best way of doing this, and it might be that you have to cut a couple of wheels or three maybe with small alterations, because it's quite unusual for the actual wheels on an old clock like this to perfectly agree with the theory. But we're going to run through the theory anyway. But from this picture you can see very approximately that the diameter of the wheel is going to be about 2 inches, and in fact the finished diameter turns out being very close to that. But to get a sort of better idea or a more accurate idea of the center distance, that is the distance between the two axes of the wheels, we can take the clock apart, which is what we do here. We now measure the center distance at 37.25 millimeters or thereabouts, and we know that that center distance is the sum of the radius of one wheel plus the radius of the other wheel, or the pitch circle radius of those two wheels added together. So let's do a little theory kind of calculation. So here we have our two wheels, and we're interested in the pitch circle diameter of the 60-tooth wheel and the outside diameter of the 60-tooth wheel. We know our center distance is about 37.25 millimeters. So if we double that value, we get the sum of the two pitch circle diameters. If we then divide that value by the sum of the teeth, 30 plus 60, we can get a value for 1 unit. And by multiplying that unit by 60, we then have our theoretical pitch circle diameter for our driven wheel, which is 49.6 millimeters or thereabouts. Now, as we said earlier, this is a blank disc without any teeth on it, so we need to add what we call the addendum factor. I'm going to use a commercial cutter here, and the manufacturer of the commercial cutter states the addendum factor as 2.76. I think I wrote 2.73 here, but I think it's 2.76 times the module, so that's 2.76 times 0.8 gives us the extra bit that we need to add on to our pitch circle diameter to get our blank diameter. Our blank diameter ends up pretty much as we estimated at around 52 millimeters. That agrees with what the clock appears to need, and so that's what we're going to do there. Now there is another small complication in as much as with meshing teeth and wheels, in modern work, typically the driving wheel, you normally have a wheel driving a pinion. The driving wheel tooth to tooth gap ratio is about 50-50. Now the driven wheel, in our case we've got a picture of a pinion here, can't also be 50-50 ratio because it would occupy all of the pitch circle diameter, and any tiny error in manufacturing or depthing would result in the meshing actually jamming and the clock wouldn't work. So we always have to have a gap, and that's either formed normally as part of the wheel or part of the pinion, and we do that by making the tooth or leaf to gap ratio 60-40 rather than 50-50, and this creates what we call a backlash or some free play between the two gears that allows the clock to run. So we're going to cut our wheel, but we're also going to cut an extra bit. So we'll cut it once and then we'll cut it again, sort of shaving off a tiny part extra, which will give us about a 60-40 tooth ratio. Doesn't actually massively matter as long as there is clearance, and of course as long as the tooth is strong enough. Now in this case all the wheel has to do is to drive that little date wheel, so it has very little work to do. So we need some way of dividing the wheel by 60. And one way I like to do this is by direct division. So that's to take a homemade or a commercially made dividing plate and use this as our indexing mechanism. Now I have two here, and as you can see, one has 59 teeth or holes on it, and the other one has 61 holes on it. So I've got no way of dividing 60. But there are always ways round this, and as I say, we could make our own division plate. And but in this case, because I'm using the Myford lathe, this wheel that is fixed permanently to the spindle of the Myford incredibly conveniently happens to have 60 teeth. Now I've read about this way of dividing before, but I've never used this, so we have to invent or make some way of actually locking the spindle via this wheel and indexing the wheel. And I'm going to do that by making a kind of spring brass detent. So I get my piece of brass and just sort of very quickly saw out a strip, but then I find that I need a bigger saw, and the saw I have has got a piece missing. So the next job, as always with these in these cases, is to make yet more parts. So we make a little sort of brass nut conveniently out of a piece of old material, and then make a screw or wing nut type thing to hold the blade in place. So once we have our saw repaired and the detent in place, we can begin to actually make our wheel. Now the hour wheel on the clock is about 1.5 millimeters thick. I'm going to use CZ120 or 120 brass for the new wheel, and I actually made two. The first one wasn't massively successful or neat, so I did it again. The first time I used 2mm brass, and then the second time I used 1.5. Doesn't really matter. This wheel isn't going to look old, it kind of just has to work. So we scribe out our approximate blank diameter, then we drill slightly undersized for our mandrel, cut out our blank, and then cut two in this case because I want a backing plate as well, and remove the burrs and flatten out the discs with water of air stone. And there we have our blanks on our mandrel, which I then turn down to our 52mm, and using a commercial cutter I begin to cut the wheel. Once the wheel's cut to depth, we lock the slide on which the cutting arbor sits, and then continue to cut the rest of the wheel. Now the In order to get the burrs off the face of the wheel, I could again just file it or use the water of air stone, but I want to kind of finish the wheel similar to the hour wheel. So I make up a boxwood chuck, which isn't a piece of boxwood. I demonstrate this in another video, and use a file just to give the wheel face some grained finish. And that's looking okay, so it's time to make a collet. Now the stud on which this wheel fits, or the collet fits, isn't parallel, it's tapered. These 19th century and earlier clocks are almost always like this, and the taper of that stud is a brooch taper, a clockmaker's brooch. So I use a clockmaker's brooch to remount the inside of the hole for the collet until it's a good fit. With our collet roughed out, I move over to the watchmaker's lathe and use the graver to slowly turn down the seat for the collet again until it's a really good fit. And then rivet the two components together. So there we are, there's our wheel mounted, and we can check that it actually works, which it does. It's actually, there is that tiny amount of backlash between the two components. It's pretty small, so you could either recut the wheel again and shave off a little bit more, double cut it, but increase the gap to tooth width ratio, or on the non-working side of the wheel you could just file a little bit off on every tooth. However, this is fine, it works, so it's now time to fit our pin that actually indexes the date wheel. So bit of assembly, and I mark onto the face of the wheel the approximate position of the pin, and I use a large soft iron clock pin which I file up, rivet in and file to a kind of triangular shape on the ends, triangular section, to index the wheel and test the whole thing works. There we are. So I hope that was of use. Thanks for watching, and please remember to like, subscribe, and of course leave a comment below. Thanks, and we will see you again soon.